Alright, welcome to the video on Graphical Behavior 1, Day 2. In this video we're going to extend our ideas of using f prime to determine where a function is increasing or decreasing. And what we're going to do is we're going to learn the first derivative test, where if f prime switches from increasing to decreasing, well, what we wind up getting is a local max at that point. So that's the focus of this video, the first derivative test. And for the most part, I'm going to do the increasing, decreasing behavior off camera and then focus on using that information to find our local max and min on camera. So there'll be a lot of times where we pause and work independently on this. So without further ado, let's take a look at what we got. Okay, the first derivative test is the test we use to find local extrema or relative extrema for continuous functions. And the basic idea is if f prime changes from negative to positive, what we get is a decreasing behavior to increasing behavior, and that's going to create a relative or local minimum at the point where the function changes from decreasing to increasing. Similarly, if we go from positive to negative, what we're having is increasing behavior to decreasing behavior, and that's going to identify the location of a relative maximum. So if it is positive on both sides or negative on both sides, what we wind up having is positive to positive or negative to negative. So we have neither a maximum or a minimum at that location. So in the graphs below, what we see is this sort of f prime is on this side, f prime is positive because our function is increasing, and on this side f prime is negative because the function is decreasing. And we get the same sort of scenario here where on one side of our graph f prime is positive, f prime is negative on that side, our function is decreasing, and on the other side our function is increasing. So what we get is our local minimum there. And finally, this one we have increasing to increasing, so our point there is neither a maximum nor a minimum. So in the last video we did the first half of example 3, so here we have it on screen. We did took the derivative, found our critical values. We have critical values of -0.5, 0, and 4. And we found the increasing and decreasing behavior. And as I mentioned, drawing these arrows that kind of show the behavior that exists helps us see what we're learning in today's lesson, and that we reach a maximum at that point. So part B becomes a very easy statement. We can say f of x has a local max at x equals -1/2 because f prime of x changes from positive to negative. And we have to specify how that change occurs from positive to negative. We can then also identify the local minimum. The local minimum is going to occur at that spot, so f of x has a local min at x equals 4 because f prime of x changes from negative to positive. So right here is pretty much the basis of what this video is about, being able to use the derivative to determine where the local max or local min occurs. And so what we now have is we're starting to be able to create a sketch of what this curve looks like using our derivative. Our function goes increasing to a maximum, decreasing, it levels out because we have a slope of 0 and continues to decrease, and then it increases. And we don't know exactly how high up on the y-axis it is for now, but we do know at negative 1/2 we have our maximum. Let's do this better. Negative 1/2 we have a maximum. At looks like at 0 we hit that flat spot, and then at 4 we hit our minimum. So our graph is starting to look like this black curve. And that kind of looks like a fifth degree polynomial. So, all right, for example 4, I'm going to do the finding the critical values and decreasing off screen, so I encourage you to pause the video now and work that yourself, and then you can check it against what I have. So go ahead and pause the video. All right, so we took the derivative, set the derivative equal to 0, used our left-hand trick to find the critical values, made a number line, and tested f prime to see that we're decreasing, increasing, decreasing. So from this we can see that we should be getting a local minimum. So we'll write this over here. F of x has a local min at x equals pi thirds. And justifying that is because f prime of x changes from positive to negative. Sorry, negative to positive. Changes from negative to positive. And then we see that we have a local maximum at 5/3. So f of x has a local max at x equals 5 pi thirds. And again, our justification is based off of the derivative, the first derivative. The first derivative changes from positive to negative. And now we need to check to see if we've answered the question completely. And the question says, find the exact values of any relative extrema. So we only found the location. So we need to figure out what is the actual value. So let's scoot this over. F of x has a local min at pi thirds. So what we do is we plug pi thirds into this equation, and we find that f of x has a local min of pi thirds times 1/2 is, we're going to go with a local min of pi sixths minus root 3 over 2. And this is important because they are asking what the minimum was and not where is the minimum. Going to our maximum, we plug 5 pi thirds into our equation, and we see that we have a local max of 5 pi sixths minus sine of 5 pi thirds is root 3 over 2. So now that we know both what it is and where it is, we could actually draw a more accurate plot of what this curve looks like, because we have the x-coordinate and the y-coordinate of the max, as well as the x-coordinate and y-coordinate of the local min. So I put that note at the bottom of the page. It's very important to answer the question being asked. So when I first tackled this problem, I just found, let's stop moving around, just found where the min and max were, but we actually are being asked what is the min and max. So pay attention. Are we finding the x values or the y values? All right, example 5, I'm going to let you try to tackle this one on your own. You'll want to find the increasing and decreasing behavior to help you identify the mins and maxes. So go ahead and pause the video here, and I'm going to do the same and write out the solution. So go ahead. All right, we ran the first derivative test, or ran the first derivative to find our critical values and see where the function is decreasing or increasing. So now we can see that there are two local minimums. They occur at positive and negative 2, and I plug positive and negative 2 into the function to get what the value is. So we have a local min of 0. And our justification, because the first derivative changes from negative to positive at these points, we have a local min. Then we can find the local max. The local max occurs at 0. So local max, if we plug 0 into the equation, we get 0 minus 4, negative 4 to the 2/3. It's not any clean number. Negative 4 to the 2/3 at x equals 0. And then we write in the justification. Okay, example 6, I'm going to do the first half with you because finding the critical values requires a little bit of prowess in algebra. So let's do that together. We're going to take the first derivative, and the first derivative is going to require us to use the product rule. So 2/3 k to the negative 1/3 times 2k minus 1. And to that we add the first times the derivative of the second. By the way, I'm taking part B out of the notes just because there's not enough room for both of these here. So, okay, from here, setting this equal to 0 is a little bit of a challenge. What we're going to do is we're going to factor out our least powers. So looking at our first term and our second term, k raised to the negative 1/3 is our least power. So if we factor that out, what we wind up having is 2/3 times 2k minus 1 plus k times 2. Because k to the negative 1/3 times k is k to the 2/3. So from there we can simplify k to the negative 1/3, and we get winds up being 10/3 k minus 2/3. We get the 10/3 k from combining this with this. And now we see that if we solve this out, we have a critical value at k equals 0 and a critical value at k equals 1/5. So now that you have that, I'm going to let you do the rest. I'm going to pause the video, so take a shot at it. Alright, so the video only wanted the x-coordinates of the extrema, which means where there are the extrema. We found that there's one at 0, which is a local max, because f prime changes from positive to negative, and then we found that there is one at 1/5, which is a local min, because f prime changes from negative to positive. Alright, example 7 is unique in the sense that if we take the derivative, because that's always going to be the first step, we find that the derivative is equal to 1 or 0. And if that's the case, the derivative, we can't use the first derivative test for the extrema because we don't have a possibility for the derivative to change from positive to negative. It's either positive or 0 always. So what we want to do is we want to take a look at this graphically, and x plus 3 looks it jumped. X plus 3 looks to be something kind of like this. We have a hole at 1, 2, 3, and at 1 we jump up to a value of 2. So there's what our graph looks like, and we can see graphically that we have a local minimum at x equals 1, because immediately to the left we are above, and immediately to the right we are above. So we approach this graphically, we say that f of x has a local min of 2 at x equals 1, and the justification, we cannot use the first derivative test. So this justification is a little bit harder to write out, but the reason for this is because as we approach 1 from the left, our function is greater than f of 1. And as we, let's not write sense. And as we approach from the right, as we approach our function from the right, we are also greater than f of 1. So basically this is saying to the left we are greater than 1, and to the right we are greater than 1. Not 1, but f of 1, which in this case is 2. You're not likely to see ones that require this justification. I know it doesn't show up in the homework, but it is good to think about other ways to justify. So, okay, let's tackle example number 8, and then we'll be done. For example 8, I'm going to leave a lot of the upfront work to you, but we'll talk about the concluding statements together. What we find here is that on 8 we have no critical values because there's no spot where the derivative is equal to 0 and the function exists. But we do have a discontinuity at x equals 0. So we're going to put that on our number line chart and see that the function has a derivative that's negative and a derivative that's positive. So one would argue that we have a local minimum there, but because the function does not exist at 0, because x can't be 0, there is no local minimum. So what we have is essentially we have a curve that's coming down and then doesn't exist and then goes back up. So, and actually if we think about this, this function reduces to x squared plus 1 where x is not 0. Anyways, we draw the conclusion there are no local extrema. So we can't identify them at all. Taking a similar approach on part B, we take the derivative and set the derivative equal to 0, and we find in part B that there are critical values at x equals plus and minus 1, and we have discontinuities at x equals 0. And when we draw our number line chart for this, we get negative 1, 0, and 1. Our function goes positive, negative, positive, negative. So we have something like this. But our discontinuity is at x equals 0. So this is not a minimum. And we only have local maximums. So we identify that there is a local max of we just need to identify the x coordinates. So local max at x equals plus and minus 1, because our derivative f prime of x changes from negative to positive. Sorry, positive to negative. From positive to negative. And there is no local minimums because the function does not exist there. I'll include a photograph of my notes so that you can see a more complete presentation, but I know I cruised through this one quickly. So here's a photograph. All right, that should wrap it up. Thanks for watching. Okay, thanks for watching a video on graphical behavior. Hopefully now you can use the first derivative test to determine where a local maximum occurs or where a local minimum occurs.